My name is Jan Fleckenstein. I'm from the Helmholtz Center for Environmental Research in Leipzig in Germany. And as I wasn't sure exactly what the backgrounds with respect to groundwater surface water interactions are in the group, I'm going to start out quite broad by first outlining some major types of groundwater surface water interactions, and also have a few words on why should we actually care about groundwater surface water interactions. What's the relevance of that process? Then I'll have a brief, relatively selective and not at all comprehensive overview of some methods that exist to quantify groundwater surface water exchange fluxes. And then I'll move on to some work that we've done on simulation of flow and transport in the Hyporheic zone and how that relates to the attenuation of pollutants and nutrients in the Hyporheic zone. And as well, give a little insight in some work we did on the effects of sediment heterogeneity on those processes. And finally, I have a slide where I'll try to summarize some of the major things that I said in some take-home messages for you. So if we look at groundwater surface water interactions, and this is shown here for an example of a river, we can actually see three major types, being the situation where the groundwater heads are higher than the stage in the river, and we have influent conditions, a gaining stream receiving groundwater. The other thing, if we have a different or reversed gradient with lower heads in the groundwater, we have a losing situation, which can, in very dry environments, and if we have a low permeable stream bed layer, turn into what we call hydrologically disconnected stream. So that basically an unsaturated zone develops underneath the river, and the stream is kind of perched on top of the regional groundwater system. Another kind of extra form of exchange can also be bank storage effects, which are driven by changes in river stage. When the river stage is high, we press water into the banks of the river, and when the stage goes down again, this water returns back to the stream. And that can be, for larger streams, actually a quite significant process also with respect to volumes of water. And then related to those exchange processes, if we look in a little bit more detail at smaller scales, the so-called groundwater surface water interface or Hyporheic zone, we also have exchange processes that are driven by morphological features in the stream, like these little steps here in the river that create gradients, hydraulic gradients that force water to go through those banks and return to the stream. Or here also these parafluvial flows and meandering systems that water is leaving the actual channel and returns back to the channel. And that's what we term Hyporheic exchange. So the water that originates from the stream and returns back to it. And there is, this is here, these figures that I'm showing here are from a USGS circular on groundwater surface water interactions, and they had this statement here about this specific interface as being very important because it collects all the water from the terrestrial system when it moves into the aquatic system, into the river network. And this zone, this Hyporheic zone, this transition zone is also important for ecological processes. It's the home of specific species that live there also. And so the simulation work that I'll later show will focus on those types of processes. If we take another look at this groundwater surface water interface in a more conceptual way, we can see, well, on the one hand, we have the compartment of the aquifer, a very distinct feature in here. Our control is the geologic heterogeneity that we usually have in subsurface systems, which are responsible for certain spatial patterns. And the river on the other side is usually characterized by much faster time scales than the aquifer. So we have on the spatial and on the temporal scale quite distinctly different characteristics of the two systems. And then we exchange water, energy, heat, solutes between those two compartments, and there are certain processes that are taking place like mixing, like reactions, and that's why sometimes people have called also the Hyporheic zone a reactor, a biogeochemical reactor. And if we look at the overall setting that this is taking place in, then of course we have catchments also. There is catchment topography, there's certain relief on the regional scale, which is actually a primary control for groundwater surface water exchange. So where the river receives groundwater inflows as a first control driven by the relief of the landscape. The secondary local controls are then these heterogeneities here in the stream bed, and then we also have those dynamic drivers and controls that come mainly from the dynamics in the river system. So this is the kind of environment that I'll be talking about. And if we look at this, and if I go back here maybe to the catchment scale, which is where usually management decisions are made, there's also certain aspects of these processes that relate to solute dynamics and catchment. So if I want to manage, for example, exports of nutrients to the oceans, then there's two main controls by which groundwater surface water interactions affect those. One is very simple, the runoff generation processes and catchment scale mixing, or in this sense it's actually not really a mixing, but the way how different compartments from the terrestrial system are coming together in the stream. In the stream they actually then do mix and creates, for example, signatures like a discharge hydrograph, but also a chemograph that we, in some cases, have solutes that are going up with the discharge, and some others we see these dilution patterns, and that's very often driven by how I mix together compartments from the subsurface and from the more shallow event flow domains. But this is something that I'll not really talk about very much. I'll be focusing more on this work down here, which is the other main control, which relates to this idea of the hyporheic zone of being to be a reactor. So the transition zone is an attenuation zone between groundwater and surface water. And you may have seen those papers also on what is called riparian buffering, that often riparian zones with waterlogged soils are a good zone to attenuate groundwater-borne solutes like nitrate from agricultural fields, for example. But then also the hyporheic exchange and bank storage cause a certain level of in-stream attenuation of water that is already in the channel network. And this is what I'll be talking about with my simulation examples. But before we go there, I want to briefly show you a few methods. I mean, this summer school is a lot about methods also that exist, and they're actually very simple, and I'm sure that most of you are familiar with most of them. And we can generally distinguish between direct measurements and indirect measurements of exchange fluxes, while the direct measurement is actually the only one that I really know of, is these very simple devices called seepage meters. It's basically a barrel or a cylinder that you press into the sediment, and with a hose and a bag you collect water that either goes in, or you measure water that goes from this little bag into the seepage meter to get the flux in either one of the directions. For the indirect methods, there's Darcy-based methods that work on calculating or measuring hydraulic gradients and conductivities, and then basically on a Darcy, with a Darcy law, we can then calculate a flux or a vertical component of the flux mainly, as we usually measure the vertical gradient. But then there's also temperature-based methods. So this is kind of shown here that you have thermistors or temperature devices or a DTS cable, let's say in a borehole, and you can measure vertical profiles and invert the advective component of the heat flux. You can basically get the advective flux from that as well. And just to give you an example, this is from some work that we did at a lake. This is seepage meter measurements at different locations here in the near shore zone. And all these dots refer to measurements from these seepage meters over about a year period. And if the flux is above 0 here, then we have an upward flux. If it's below 0, it's a losing flux. And you can see here the gray line is the water level in the lake that fluctuates due to manipulations that we did. And you can see that those fluxes then also go up and down depending on what the water level is. But you can also see that there are some locations like here, for example, where regardless of the variations in water level in the lake, the fluxes are relatively constant. I mean, the problem with the seepage meters is, where do we place those? I mean, you have to have an idea roughly of where the music is playing. So another way to actually map exchange patterns would be temperature measurements, taking advantage of the fact that in the winter the water at the lake bottom is at 4 degrees centigrade, and then the groundwater in most regions of the world is then warmer. So upwelling would be anomalies in the temperature patterns. And so you can put in a DTS cable, for example, and this is shown here, one array that we put in there, some seepage meters that are close by. And you can see here the temperatures that we measured there, and compared to that, these seepage meters that are close by. And you could, for this system, pretty nicely see that we have a losing to neutral condition at the southern end, a moderately to strongly gaining area with these hotspots with very high temperatures, and a moderately gaining situation here. So basically the losing here is indicated also by these low temperatures. This was done in December. In winter, when the water at the lake bottom is around 4 degrees. And so you have these very low temperatures here, whereas here they're modulated by the upwelling groundwater. Another way to use temperature would be measuring these vertical profiles. And one device that we have worked with in the past is these, like a steel rod that has different temperature sensors on the vertical. And there's analytical solutions to the 1D heat transport equation, like this one shown here, that you can then use to get a snapshot of what the flux would be, assuming that it's under some kind of a steady state at this point in time. And then you can get something like this, that you can actually do these roaming surveys. You can go along the river, you can pound this thing in there, wait a while for the sensors to equilibrate in the temperature, and then you basically get this vertical flux here by fitting the observed to the temperatures to this model. Oops. The one thing, oops, sorry, out of control. The one thing, though, that is a little tricky with this method is you make certain assumptions about the flow being predominantly vertical. You also assume the subsurface somewhat to be homogeneous. But we wanted to understand how important are these assumptions if you violate them. So we did a bunch of simulations to look at non-ideal conditions and how that would affect those types of measurements. So what we did here is basically a 2D model that includes some heterogeneity, shown here as binary fields. Then we simulate flow and heat transport through the system. So you get these temperature distributions, and then we sample for each column of the model the temperatures that the model, which is our virtual reality, produces, and then fit this analytical solutions to it, and then compare the simulated versus the calculated, basically simulated being the virtual reality, what we assume to be the real situation with all the variability and flow vectors, and then the calculated ones from this analytical method. And you can see in this case for somewhat vertical, I mean the forcing here is vertical flow, whereas here we have an angle of about 30 degrees that we do shift the two signal or the two curves a little bit, but overall we do get the patterns quite nicely. It's more problematic if we have larger contrasts in the conductivity. So this is the conductivity contrast in these binary media. In this case, 3 orders of magnitude versus 1 order of magnitude. And here you see that if this contrast is very strong, and this is for like 50% proportions of the two materials, then you miss out some of these hotspots that exist just from the structure of the heterogeneity. But if, for example, this proportion here changes also, then you can see here if it's 90% low conductivity matrix and then only very few high conductivity zones, then actually for those cases we looked at, it matches very well again. So we found that we actually could get quite good estimates over a surprisingly large range of non-ideal conditions using those methods.
Is the hydraulic conductivity?
What's that?
K
K is the hydraulic conductivity, exactly. Another one, and this is kind of another method with heat that we've been working with, and this is a device that we proposed in 2011 here, is this it's like active heat methods where we have a heat emitting point here, a heat source, and then a cylindrical array of temperature sensors around it that you can put into the hyporheic sediments to get these small scale flow vectors in the hyporheic zone. And this is just an example from a small river in Germany showing the directions of the flow vectors, and the colors refer to upwards to downward fluxes, blue being downward and yellow, the yellowish colors, the warmer colors, upward. You can see that over a very small range you can have all sorts of flow directions. So depending on what the morphology of the streambed is, heterogeneities in the sediment, you get a lot of very complex flows that have very little to do at first sight with the regional forcing. If you would take a groundwater well and then the stage in the river and try to estimate the exchange fluxes. Of course, all these methods that I've shown so far have been kind of point measurements. There's also integral measurements, and I'm just picking out one here that we've worked with a little bit. It's using Radon 222 as a natural tracer to get net groundwater gains over larger river reaches, with the assumption that usually groundwater has higher radon concentrations because it had more contact with sediments that emanate the radon. And then we can basically use this equation. It's a modified version of one that Peter Cook had proposed in the past. It's a radon activity balance, basically. The C for concentration in this case stands for activity in becquerels per kilogram. So this is basically the balance that accounts for the groundwater influx. So what comes in, this is basically what we want to get at the end. Then you have a degassing component, radon that in the stream is degassing. You have a decay, natural decay. And then you have effects of the hyporheic flow also, water that goes into the sediments in the stream, and there also radon is emanated, and there's also radon decaying. So you have the decay terms in here and the emanation terms as well. And then, of course, you have to account for inflows from tributaries as well. And then you can get most of these things from either measurements or from the literature. And in this case, in our application, we fitted the observed radon concentrations or activities by changing this H and the TH, and the H being the depth of the hyporheic zone. Yes?
You're in Laplace space for time.
Repeat it?
You are in Laplace space for time. Is that right? Your Laplace is in the time period. That's why you have the 1/1 of the thing. Yes?
No, the lambda here in this case is the, I have to look, this is the decay coefficient. So it's no transformation, it's just a, so it's not a Laplace transform kind of thing or anything.
So are you in equilibrium?
Well, this is making the assumption that this is in an equilibrium over a stream reach. It's basically a mass balance or activity balance for the radon. So it's like a mass balance equation or continuity equation. And so what you get from this is then that if you take those measurements along a stream, you can get the influx rates per unit length of stream here in meters squared per second. And what I want to show here is that you often can see that in this system, for example, where the main groundwater inflows are occurring, we also get a lot of nitrate inputs from those agricultural areas that load the aquifers with nitrate. Of course, we can also model groundwater surface water exchange, and that's often a very convenient or nice way to look at those processes because you can then use the models also to play with the boundary conditions, and you can try to learn more about your system. The traditional way of including surface water in larger regional groundwater models was very coarse though. So you usually have coarse numerical grids like here for a regional model, and you would define some kind of a line element that represents a river as a Cauchy type boundary, a third type boundary condition. So you're basically interested in how much water is exchanged between a larger groundwater body and this river or surface water feature there. And the way how it's represented, it's with a simple Darcy flux also, where a situation like this, where the streambed material and an aquifer material is represented in a simplified way through this rectangular channel, and then the flux is calculated as the head gradient between the river stage and the groundwater head in the model cell times the conductance that is defined by the thickness and the conductivity of this streambed layer. The problem there is that it's relatively coarse and you cannot really resolve smaller scale patterns. So if you're interested in certain ecological aspects, this is not the way to go. And this is originally was used for things like larger scale water balances, like conjunctive use scenarios, groundwater recharge estimates for regional aquifers, for example. Of course, you can also go in a little bit more detail using some of these integrated surface-subsurface models like PowerFlow. I know that you've done some work here in this course with PowerFlow also, or hydrogeosphere, that usually have some form of the Saint-Venant equations or some approximations to them for the surface flows, and then in an integral solution, solve that with the 3D richest equation for the subsurface, and then you can get also exchange fluxes at smaller scales. And the example that I'm showing here is from Canada, where this is the modeled exchange fluxes here and the colors across the stream channel, and these are estimates over the same reach that were made based on temperature. So you can see that some of these features you can pick up also in the model and calibrate your model to that data. If we go one step smaller even and go to the Hyporheic zone, it's important to make a distinction between features in the streambed that are non-submerged and submerged features, because usually if we use something like Saint-Venant or those equations that give us a hydrostatic pressure over our streambed surface, we do not account for this velocity head, which usually if we have an in-stream feature which is not fully submerged, then usually the gradients that drive the flow through these features are mainly hydrostatic, because we have water level differences. In this case here, it's an in-stream gravel bar between these two side channels. But if we go to something where we have very small features at the streambed, and when the depth of the water is very large compared to the amplitude of those features, then this term becomes important, because then we don't really have a lot of hydrostatic pressure variation across those features, but we still get flow through them, which is driven by dynamic pressures that develop here at both sides of these structures. And this is shown here. Then you need something like a Navier-Stokes model, like open foam, for example. I think tomorrow you'll hear some more about open foam that would then calculate those turbulent flows, and then you can basically map the pressures that fall out of this simulation onto a groundwater flow and transport model. And this is what we did also in the examples that I want to illustrate now. And the idea or the motivation of this was, or can be summarized by this one paper that in 2005 termed that the Hyporheic zone is a river's liver. The idea that I had alluded to earlier, that we have usually mixing of chemically different waters, resulting from that pronounced gradients in the chemistry and temperatures, And we usually also have enhanced microbial activity, so good conditions to turn over material. We also have increased residence times compared to the residence times in the open water. And often we have sources of organic material from the stream that are delivered and that can fuel reactions. And so the idea here is to look at, or what we wanted to understand, is how structures like pool riffle features, like those exchange flows that are produced along those features, how they affect turnover of certain solutes. And we mainly were interested in nitrates. So the other thing, though, would be that if you have groundwater that flows into the stream, it has to also pass through this zone that is usually chemically somewhat distinct. So we can distinguish two different types in a way. We can have this bypass flow, or when the hyporheic exchange zone is basically in parallel, so only a certain amount of the river water goes through this zone and then comes back to the stream. And the situation where along the flow line it's in series, that basically all the groundwater has to go through there. And for the first case here, the important thing is, if you're interested in attenuation of stream-borne solutes, what's the hyporheic exchange length? How long does my river have to be, assuming that this is a constant process along the entire length, until theoretically all the water in the stream has been cycled through the hyporheic zone once, and that then could determine how efficient the reactor is. So what we did is we simulated this idealized pool riffle sequence here with a sinusoidal form, and this is the center line of a stream. The amplitude is the highest at the center of the stream, and then it kind of decreases towards the bank. And we looked at different morphologies defined by various different amplitudes of those structures. We looked at differences in discharge, the flow that goes through the stream, and also one very important aspect, ambient groundwater flow. So how are these processes affected by this system being embedded into a regional flow system? So in this case, represented by upwards or downward fluxes. So basically those two conditions that I showed earlier implemented via a boundary condition. And this is just an example from one of these features from those simulations for the highest amplitude here in this case. And the colors refer here, these are all flow lines through the hyporheic zone. The colors refer to magnitude of the velocity. The negative ones are downward directed. The blue ones are upward. So you can see it's going in very fast in some infiltration zones. And then it comes out with a relatively high velocity again at those exfiltration zones. It slows down in here. But you also have usually these reversed flow cells. The direction of flow in the river is in this case in this direction, where you have some milder infiltration zones there. But you also see that there is flow lines from the groundwater that come in, that go into the channel. And you have some where water that downwells never returns to the stream also, depending on what those fluxes here are or what the regional gradients are. So you usually get these typical flow cells. And this is the zone within which you can, theoretically at least, attenuate solutes that are in the stream. If we look at this again for different conditions, this is showing gaining in blue, losing in red. Same morphology again. And this is just different magnitudes of the upwelling or downward flow at the lower boundary. And you can see in both cases, if the upward flux becomes higher, we start to suppress those flow cells just because the dominance of the regional gradient is so large. And a lot of the water that flows into the channel actually is derived from the groundwater. So we have only very little flow cells. The same way, though, with the losing conditions. If the losing gets stronger, then a lot of the flow that goes into the sediment just never returns to the stream. So in general, we reduce the amount, the area of our flow cells by having those groundwater interferences. In our simulations, or what we looked at, we had median residence times in the hyporheic flow paths between 0.7 and 19 hours, so time ranges over which we can expect certain reactions to take place. If we look at the magnitude of flux, this is the total flux through the hyporheic zone. This is all steady state simulations. The solid triangles are high flow in the stream, the open ones lower flows, and then we have here again neutral conditions, so practically no net gradient between the regional groundwater and the stream, and then losing and gaining, increasing in both directions. What we can see is that in general, the higher the flow is, the larger is the exchange, the larger are these pressure variations that we create. But we can also see that if groundwater does not interfere under the neutral condition, we get the largest flux and also the largest hyporheic zone. If we look at the efficiency, or not the efficiency, but the ratio between the flux through the hyporheic zone and the total flow in the stream, Then it's a different picture. We can actually see that for the solid circles with the high flows, we have a less favorable ratio. So less of the total amount of water that goes through the stream actually cycles through the hyporheic zone. So under low flows, we can move more of the water through it. The total volume, of course, is larger when we have larger flows because we're just having larger magnitudes of flow. And we estimated from our scenarios that this ratio here was between 1 over 10,000 to 1 over 100,000, which translates into a hyporheic exchange length of 10 to 100 kilometers. So basically, you would need 10 to 100 kilometers of river to theoretically have all the water go through the hyporheic zone once. So that's a very low value. This already kind of hints at the capacity of this zone to attenuate. So the next step was then to look at the reactions, the same kind of scenarios, and we made certain assumptions about the solutes. In this case, we simulated nitrate coming from the stream, oxygen saturation in the stream, and a significant source of DOC in the stream also. For nitrate, we have a nitrate species upwelling from the groundwater, which is we treat as a different species to be able to distinguish between the two, and we make the assumption in this system that the groundwater has no oxygen and practically no DOC. The reactions that we represent are aerobic respiration that consumes the oxygen by respiring carbon, and then denitrification, which sets in as soon as the oxygen has been depleted sufficiently. And so these are just some examples from those scenarios or the simulations. This is turnover rates or consumption rates in millimoles per liter per day. Red being higher values, blue being lower. Aerobic respiration, you see under neutral conditions, you have a relatively large exchange zone and you very efficiently respire the carbon and reduce the oxygen. And then underneath you have a zone here with very active denitrification because you still have carbon and you are sufficiently depleted in oxygen that you can denitrify. In this scenario for neutral flow, there's no groundwater upwelling, so also no groundwater that can be denitrified. Under the gaining condition, you can see that it's the same thing. The flow is a little smaller. It gets suppressed again, or the cell here gets smaller. And then I have a smaller fringe of denitrifying zone underneath. And then also underneath this zone, another zone where the groundwater that upwells can also denitrify because it hits a zone where the conditions are right for denitrification. Under losing conditions, of course, we press the water deeper into the system and the respiration zone gets larger. And we only get denitrification of streamborne nitrate in deeper zones. And if we look at the effects again of the gaining and losing conditions, you can see that this is here what we call efficiency of denitrification. So it's the ratio between nitrogen consumption and nitrogen influx. And again, over the range of losing to gaining conditions. Again, we see that the most efficient removal is done when groundwater does not interfere very much. And then it almost symmetrically kind of declines if we have gaining-losing conditions. For the groundwater-borne nitrate, of course, we only have under gaining conditions the same way, most efficient if the groundwater upwelling is not very strong. The similar kind of thing we did also for in-stream features. And this is like one of these features here, an in-stream gravel bar that we looked at. And we had some these mini piezometer kind of things in here with EC loggers, and so we could estimate residence times in this feature, in this gravel bar, based on electrical conductivity time series. We have natural variations in the stream, and we can follow those signals into the sediment. And this is one thing we use to also constrain our model more. We use the same kind of software, OpenFOAM, for the surface flows over a range of the different discharges. You can see here that under the higher discharges, these features start to get submerged. And then we take again the pressure variations at the stream bed and put that onto a groundwater model, which is sitting in this domain here of the surface model. But the groundwater model is larger to account for the regional groundwater flow system to also be able to play around with groundwater flows, ambient groundwater flows. The same reactions again, same kind of story. And this is what the results look like, or one snapshot of it. This is a little busy graph here, but this is again neutral condition, the upper row, gaining conditions, losing conditions. The dots here refer to the beginning or end point of flow cells in the flow lines in the subsurface. The blue being hyporheic exchange fluxes, dark blue being inflow, the light blue upwelling. So it dips down into the sediment here, comes up on the other side. The green dots are gaining flow paths, so they are flows that come in from the groundwater and are not derived from the stream, and the red are losing flows, stream water being lost to the groundwater. These are the directions and magnitudes of the different flow directions that we have in these gravel bars, and then here we have aerobic respiration and denitrification, and I don't want to get into detail here, but you can also see you always have a very broad or bigger aerobic respiration zone at the top, and then as a fringe underneath you have these denitrification zones. If you have gaining flows, all those zones become somewhat suppressed. And under the losing conditions here, we have a very large aerobic respiration zone, and then in the deeper system, some areas where we can also denitrify. And if we look at the efficiencies again, we see the similar picture here, that also the most efficient the most efficient removal can be done when the groundwater influence is the least, because then we can develop the most pronounced hyporheic flow cells. One interesting thing, though, is here for those non-submerged features that the variations in discharge don't really play so much of a role, because the hydrostatic pressure difference gradient across those features does not change so dramatically over the different flow conditions. If we look at the denitrification, sorry, this was for aerobic respiration, by the way. Sorry, this is denitrification of stream-borne nitrate, and this is again just the efficiency, so the ratio between how much of what is received can be removed. And there we see, in this case, actually interestingly, that the efficiency increases with the gaining flux, which does not mean that more is denitrified. It's just the efficiency. If the gaining flux gets larger, we have less flow through the hyporheic zone, less water going through it, but this little flow is denitrified more efficiently. Another aspect, and that's the last one that I have here from the simulations, is the effect of transient stream flows. We were interested in what happens in a stream. We usually don't have steady state flows, we have flow events. So we looked at a transient scenario where the colors along this hydrograph, so this is a stream flow hydrograph, indicate the colors of the flow lines that are initiated during those periods of the flow event. So when the stage is very high, when we have the peak of the event, we press the water very deep into the subsurface, and we send it out on path lines that are in the very deep hyporheic zone. And they return later to the stream, much later than when the event in the stream has already passed. So we basically create this pulse of water into the sediment, which increases the potential for denitrification. And so we had different scenarios here, and I just want to look at this one, where we assume unlimited DOC source from the stream and an increase of the nitrate concentration as the discharge goes up, which is something we often observe in streams.
Do you assume, when you affect your particles here, you assume that the discharge is fixed? Because the color of the line should change with time, or it's one streamline has one color?
One streamline has one color in this case. It's just referring to when during the event it started, and then it's followed all the way through.
Yeah, but I mean, if you go deep into the bed, and then the flow discharge just slow down, so you won't go back, no? You will have a different trajectory.
Oh, I see that. But that's okay. Yeah, I see what you mean. But this is accounted for. This is basically in the sense that how they change. If you're right, if you were staying at the high peak all the way through, then you would have even deeper flow lines here. I mean, the whole flow field obviously changes again because the forcing from the pressure changes. That's right. But it's that's included in here in this representation. So it's over this transient event. Yes. And basically what you can see under each scenario, that if the duration of the event, the flow event in the stream, and the magnitude increase, then we increase also the denitrification efficiency by pushing the water into those reactive zones. Okay. The next thing that we wanted to look at, and this is some other work, was the effects of heterogeneity. Stream beds also are not usually homogeneous, so we had a project with some colleagues in Israel, and they have a nice flume where we can also mimic groundwater upwelling and stream water downwelling or neutral conditions. And we basically geostatistically simulated heterogeneity fields, packed those into the flume, and then ran those scenarios by putting dye into the surface water. And this is a little animation that I'll start, and you'll just see. So this is basically gaining situation, neutral, losing. Here are the fluxes of either gaining or losing, and then the stream water velocity in the flume. And you'll just see how the dye goes into the sediment. Just start this individually. Oops. Okay, this. So you can what you basically see is, as we saw earlier from the simulations, that if we have gaining conditions, it's over already, I think it's going to start again, hopefully, but that the zone of penetration of the dye is, relatively small. I'll start it again. Compared to those situations where we have neutrals, the heterogeneity brings some of the stream water deeper into the system, and of course under the losing, it's just a matter of time until the whole domain is occupied with the stream water. So you can see those effects also experimentally. What we then wanted to look at was the idea of how does it affect the residence times in the hyporheic zone and the total hyporheic flux, and also the reactions. And for that we did some modeling experiments again, where we geostatistically simulated random fields, multi-Gaussian and indicator fields, and looked at about 10,000 realizations to evaluate the effects of different correlation length and angles of the depositions here. And for the forcing, we used an analytical solution by Elliott and Brooks that gives us the sinusoidal pressure variation that then drives the flow through those sediments. And basically what we observed is that as three major effects, that the hyporheic flux gets magnified. So basically this is the distribution, and the yellow is the reference homogeneous case, and then the blue is the heterogeneous, and those are all the different realizations. And as we increase the intensity of the heterogeneity, represented here as the variance in the hydraulic conductivity, we increase the amplitude of this, the distribution of the hyporheic flux, and we decrease the mean residence time. So we actually increase the volume of flow, but we move it through the system faster also. Another thing, of course, is also that we spread the distribution, as you would imagine, over a longer range of times. If we look at the denitrification and similar reactions, again, sequence of aerobic respiration and denitrification, this is the example of a homogeneous domain. And you see the greenish colors are the high values. You have those zones, as we saw in the previous simulations, those fringes where we denitrify. If we go to the heterogeneous case, we see that we get those features that are locally different then, depending on where the flow funnels the water into the deeper system. And if we look at different scenarios here with different structures and other angles also, we can also create these effective denitrification zones in the deeper hyporheic zone. So basically, hyporheic flow is affected by heterogeneity in many different ways that are also counterbalancing each other. So for example, if you reduce the residence time, then you have less time for the reaction to take place. But if you move it deeper into the system, there's more favorable conditions. So it's basically the interplay between those things that result in how much you can remove from the stream water. Yeah. Yes. So I'm coming to the end. Thanks for the hint here also. So to summarize from this, I hope that I could show that, well, groundwater surface water exchange takes place at many different nested scales. So it's not really easy to say this system is gaining, losing. It really depends on the scale that you're looking at. The exchange fluxes can be quantified using various direct or indirect methods. All have their merits, but also their faults, like with all methods. The main primary control or driver of the exchange flow is obviously the pressure variations at the stream bed, which are caused either by hydrostatic pressure variations predominantly, or also by dynamic pressures, but that depends on the type of features. Losing and gaining conditions work against the primary driver. So if you have strong upwelling, then this will subdue the hyporheic flow cells. But it also diminishes hyporheic exchange flux, also the extent, the size of the hyporheic zone, and the residence times, of course. The reactive potential in the hyporheic zone is mainly controlled by the extent of the reactive areas within the hyporheic flow cells and the associated residence time. So basically this counterplay between residence times and where you are in the system. Our modeling suggestion, but that's only for this one river system, which we think is representative for other rivers as well, but it's of course not for all the rivers, but just as an example, that if we account for these different processes, pool riffle structures and those in-stream gravel bars, under ideal conditions, meaning very little groundwater interference, we could remove up to 8% of the nitrate load in the stream over 1 kilometer of stream section, which under such conditions is not so little. I mean, it's not a lot, but it's if you think of other processes that also take out nitrate, it's actually not too bad. But some other cases it might be like 100 kilometers, or only very less than 1%, for example. Then of course it's negligible. We could show that events temporarily increase the removal efficiency of nitrate, and in our simulations this was up to 3.6 times larger values if you had this pulsing from the stream stage going up and down. So if you think of climate change, changes in variability of flows, that might affect also attenuation. Streambed heterogeneity increase the hyporheic flux and the width of the residence time distribution, but the mean hyporheic residence time decreases. And this may reduce the potential for denitrification in the shallow system, but at the same time it may promote denitrification in deeper parts of the system.
I question your approach in having statistical fields because these are ripples and these are clearly sedimentary structures. So we might have more heterogeneity there. These are different connectivities. So my question is, have you done studies of this or whatsoever?
Well, it's a good point. Of course, the question of how is the heterogeneity of a streambed is not an easy one. There is some work by people from the US who have looked at this more from a genetic point of view in a braided gravel bed stream, and where you basically have the structure of the heterogeneity field more on the basis of how those stream beds are formed and transformed by flow events. But the general findings that they have, for example, are very similar to what we find. I mean, then there's some work by Yannick Cardenas where they looked at outcrop analogs, where they used basically old fluvial deposits, consolidated deposits, and kind of map the structure there onto their flow simulations. Also somewhat similar results, but it is very difficult to really say what the heterogeneity of a streambed is. So the way how we went about it, it's not binary fields. It's like the indicator fields, they can have as many as 3, 4, 5 different hydrophases that you account for. But the question of what are the angles, what are the length, are they, and I think you could probably spend another 20 years on, I don't really know of a lot of work on this that really says this is how the structure of a streambed is. So we rather decided to try to cover as large a range of differences and look at what the effects are than try to represent the perfect or right streambed, which I don't think really exists. Yes?
What about the particles you mentioned, if in this case it's the river that provide the water to the aquifer? I mean, can play a role in clogging the system or?
Oh, you mean like clogging processes?
Yeah.
Yes, absolutely. And this is something I didn't show anything about, but we've done some work also that looks at effects of biological clogging by those processes, because when, for example, in the summer the stream flow gets very low and you have a lot of nutrients in them, then there's a lot of potential for biologic activity, and so you have biofilm growth in the upper parts of the system. I have one paper out there on this which shows that there is interesting feedbacks between the amount of flow reduction by this bioclogging and the feedbacks onto the processes of how much the biofilms grow and so on. So that is definitely a process that happens in like mechanical clogging from sediment, of course, is another thing that would happen. For the system that we worked on, it's not so an important process, but obviously also flow events remove all the sediment and set everything to zero, so there's a lot of more complex things in the real system. So this is more like the idea to try to isolate certain things and understand this better, and the real system usually is yet another level more complicated, I guess. I hope that answered your question. There was one over there also earlier, but maybe this is...
Yeah, my question was in a similar direction what we asked before. So you looked at one particular river with a certain gravel size. I just wonder if one could combine the simulation that you did on hydrogeneity with work by, like which gravel size and which flow conditions are likely to produce which kind of ripples and which kind of, because I think there's probably certain heterogeneities that you could model, but won't occur, they're not stable in reality.
Yeah. No, absolutely. I mean, but the examples of the heterogeneity was a different system. This flume system is a sand bed whereas the real river where we modeled or calibrated our models to is a coarse gravelly thing. But in this case, the coarseness of the material only comes into the conductivity of in the simulation. But of course, for the flume, for example, you know if you increase the flow a certain amount, then the bed is not stable anymore, and then the things start moving. And there is some work that looks at that also under what kind of flow conditions, which structures evolve and how stable they are. That of course plays into that as well, and that would be an interesting thing to follow up more.
So you have shown some conditions, for example, gaining or losing water is more favorable for matter turnover.
Mm-hmm.
I just wonder, in reality, is there some artificial solutions that is based on the conclusions that you got in this study to increase the natural attenuation
Yeah.
of the contaminants, and think they're practical in,
Yeah, I mean that would be the idea, to say exactly if you do restoration, for example, you have certain assumptions about what is creating a better environment or a more pristine or closer to pristine environment. And from an ecological point of view, often the morphology is one aspect, which obviously also increases exchange. And we think that, for example, this one aspect of groundwater connectivity is usually not accounted for. So in some ways, you could say that perhaps you could get more bangs for the buck if you do this morphological aspect with the idea or the goal to increase attenuation, if you know that you don't have either strongly losing or gaining section of the stream, those kind of things. But I think it's very, very difficult to really argue in a simple way that is really accessible to application, because in the management, they usually want very clear and simple answers. And I understand why. I'm not criticizing this, but it's very difficult sometimes from the work we do to come up with something that is meaningful and that is not just empiricism, and to really be able to say this will have this effect. But I think this direction, definitely, we've thought about this, and there's other people thinking in that direction as well, that you can structure your stream beds in a certain way to increase certain ecosystem services from the system.